Right, let's start. So this is about time stepping, and the issues are, as always, what is the accuracy? Is it, if there's a time step of little delta t, is it delta t or delta t squared or delta t cubed accurate? There's questions of stability. If you take a large delta t, the solution can blow up. There's also an issue of the cost. So there are three elements of cost. There's how long does it take to run, the CPU time, which is the CPU time per step times the number of steps. So it's very typical that a first order time stepping will need lots of steps, but it doesn't cost much. One step is quite simple. If you have a more sophisticated time stepping method, which is second or third order accurate, each step is much more complicated to calculate, but you don't need so many of them. So there's a sort of compromise to think about there. Also, the more sophisticated ones do tend to use a lot of memory of the computer, although these days memory seems nearly infinite. But we can always ask for a bigger problem, so we can easily fill memory. And finally, there's your time. So the simplest thing doesn't cost much time. It gives you roughly an answer, and it may be worth waiting for the calculation to run for 20 minutes rather than being instantaneous with a more sophisticated one, because for you to reprogram it, it could be several hours of effort to reprogram to a more sophisticated one. So these various costs. Okay, so I'm going to forget about spatial discretization. So I've talked about finite difference, finite elements, and spectral methods. So we take our governing equations, like the Navier-Stokes equations, and we turn them into an equation for the time evolution of the amplitudes, either the spot values at a finite difference grid, or the amplitudes of basis functions in finite element or spectral methods. And this is all about those amplitudes changing. So this u is a big vector. It could be 10 to the 4th unknowns, which we're time stepping forward. And we're going to think about the time integration as a black box. We're going to try and make a time integrator, forgetting about anything we know about spatial discretization. So there is another approach which worries about the discretization and using some information about the discretization. And that could be helpful for you. But it tends to be you can only do that with finite differencing. You can't do it with spectral and finite elements. But I'm not going to do that. I'm going to say we have these Fourier amplitudes. We want to know how to time step them with different schemes. Right, stability. There are various degrees of instability. It can be an algorithm which is totally unstable, and that is obviously not going to work. Typically, if you make the time steps smaller, they blow up even faster, a bad scheme, and it tends to oscillate between plus and minus large numbers. There are conditionally stable schemes, which means as long as delta t isn't too big, it works. And that's the normal case. And then there are even more stable schemes. So we went unstable, conditionally stable. There are unconditionally stable schemes, which means whatever the value of delta t is, it's stable. And they tend to be rather dangerous. So you shouldn't do them. They're dangerous because they're going to be inaccurate if you take a large delta t, and you wouldn't know that. And yes, perhaps not. Okay, so stable. You all think you know what stable is, but do you? There are lots of definitions of stable. So one, particularly for these differential equations, stable can mean that the numerics always decays, even if the physics doesn't. That's not very good. So we don't want that. It could be that the numerics don't decay, but they don't grow. They don't blow up. And that's a sort of a bit better than things that decay when they shouldn't. But the best thing, in fact, is the numerics which don't blow up all that much. So if you want to go to time 10, you may have to take delta t like 1 upon 100. If you want to go to time 20, you may have to take delta t 1 upon 200. So there'd be some, how far you want to go forward in time. If you want to keep the error small, you may have to take smaller and smaller time steps to keep the error small and larger times. And they're about the best, those schemes. My numerical analysis friends in Cambridge rather like type 1, things decaying numerically. They're not interested in the physics. Okay, there is a thing called the Peter Lax equivalence theorem, which says that if you've got a sensible question that's linear, and you make approximations in your numerical approximation, which is consistent, so that the error gets smaller as the time step gets smaller for each step, then as delta t gets smaller and smaller, the numerical answer converges to the analytic answer. Only if the scheme is stable. Okay, so that means you get the right answer, if it works. So that's a nice theorem to lie behind this. Of course, if it works, you're happy, so you don't want to know about the theorem. Okay, an issue in time stepping is stiffness. And to get into that, we want to think about arriving at some time t0 with the solution u0. What happens if we make it just a little, if we go forward a little time? We look at variations, little delta u's around u0, and ask how do they evolve in time by linearizing f of u. So we look at the derivative f primed differentiating f with respect to u. That's a massive Jacobian matrix, probably. And we freeze the time at t0, we freeze the solution at u0, and we ask how does this linear constant coefficient system evolve. So to find out how it evolves, you're interested in what are the eigenvalues of that matrix f prime, the derivative of f with respect to u, the Jacobian matrix. And in particular, you want to know about the biggest eigenvalue and the smallest eigenvalue. To be precise, the real part of the eigenvalue. And it's absolutely typical that there's a big ratio between the biggest one and the smallest one, and they will certainly differ by 10 to the 4. It could be 10 to the 8. And the problem is that the time step is controlled by the largest eigenvalue, and you may be interested in things that are happening corresponding to the smallest eigenvalue, which means you have to make lots and lots of time steps to look at what turn out typically to be fine-scale modes. So there are fine-scale, very fast modes that you have to resolve numerically, but they're boring. You're interested in the slow, long, large-scale modes. So under those circumstances, there is something to be said for the unconditionally stable algorithm, which allows you to take big time steps over these boring fast modes. Of course, there's another approach, is you could just not resolve these boring fast small scale modes, and you wouldn't have to resolve them. Okay. Right, so we're going to have a run through the routines, and in fact the order on these transparencies is different to the order that you've got on the handout, and there's an extra one in the middle. Okay, so the first thing, I'm going to study, because I want to talk about things, think about a one-dimensional problem now, rather than a vector u of lots of all the Fourier modes, just to have a one-dimensional, one variable u, which evolves according to a linear equation, lambda. This is one of the eigenvalues of the big problem. So how does that equation evolve? And this would be forward time stepping. From time level n, we go to n plus 1. This is the time derivative, and we're equating it equal to u at the time we started. Not the time we end, the time we started. So then we can easily solve that. and we have this solution that we take that onto this side, and we have 1 plus lambda delta t, and then we want to raise it. If we want to go to time level n, starting at time level 1, we need to make n steps. N steps is the current time divided by delta t. And if I make delta t smaller and smaller, this expression of 1 plus a little thing to a large power tends to the exponential. That just happens to be the analytic answer. So it's converging to the right answer. Okay, now if lambda up here is real and is negative, so the system decays, what you need is to make the time step smaller than 2 upon lambda. If delta t is bigger than 1 upon lambda, then the solution, the numerical solution, oscillates and decays, where the analytic solution doesn't oscillate and decay. So probably it's better to have it less than 1 upon 2 lambda. If you have it 3 upon lambda, then in fact it oscillates and blows up. So it's a conditionally stable one. In the case when lambda is purely imaginary, then you're interested in the size of 1 plus lambda delta t. This is an imaginary number, so the size is the square root of this, the real part squared plus the imaginary part squared, and that's always bigger than 1. So when we raise it to the number of time steps we're making, this is going to increase. So this is actually unstable, but it's rather slowly unstable, because you can see that when delta t tends to 0, because there's delta t squared here and to the power 1 upon delta t, it tends to an exponential which is essentially, as far as I'm interested in, delta t times t. So if you say I only want to go to time 5, I can make delta t 1 upon 5, and if it's smaller, and I can keep this small. So I can keep this number near to 1 by making delta t small enough. If you want to go to a bigger time, final time, then I have to make delta t smaller. Okay, this is a first. So this is a first order. There are errors of size delta t, and it's called explicit because to work out the new value, I need only the old value. In a minute, we'll get to the opposite, which is now actually. So this is actually, I'm jumped a bit further down your handout to the backward Euler, which is first order and is implicit. So it's a first order accurate, and I work out the time derivative, and I work out the answer at time level n using the final value, which I don't know. Fortunately for this very simple linear equation, it's quite easy for us to solve. This, we can take this onto this side, that onto that side, and get this solution. But in the vector version of this, I have to invert a matrix, and probably a big matrix, so it may not be so good. What is good about this is, if it's a stable system and lambda is negative, then this is 1 plus something, because lambda is negative, so this is going to decrease, whatever the value of delta t. So this is an unconditionally stable system. Numerically, it will... This is a highly stable system. Whatever value of delta t you take, as long as lambda is negative, it will be stable. On the other hand, if you take lambda, if you make delta t too big, you don't get a very accurate answer. So I'm taking the value delta t is 1 upon lambda, substituting in this expression and taking the limit of delta t going to 0, and instead of getting e to the lambda t, I get e to the lambda t, but times log 2. Okay, so this is a warning where I can analytically, I can calculate what happens. If you take delta t too big, because you're allowed to take delta t as big as you like, if you take it too big, then you get the wrong answer. It's a nice exponential growth, but at the long exponential rate. So they were first order errors of size delta t. This is, this is not on your notes, but the handout has got a big piece of white paper at the end. So I'll allow you to copy this down. This is, if you've coded up first order forward differencing, it is only a couple of lines of extra code to write out this Euler midpoint method. Let me explain it to you and then give you time to write it out. So the idea is you go to a half time by taking a half delta t step using forward differencing. So we go, and I'm writing it out now for the full nonlinear problem, which is when we use it. So we go from time level n to essentially time level n plus a half with a half time step using the old value. And then we use this half step value back in there and the time at the half value to work to now step from time level n to n plus 1 using a good estimate of the time rate of change at the middle point. Okay, now I've explained it. So I often use this one. It's explicit and it's second order accurate. So let me explain in terms of a picture what is going on. We're trying to go from n to n plus 1. And the first order time step will go off at this tangent direction here. And you see it's got a delta t error there. So what we do is we stop at the half point here. And then we calculate what is the slope at this point here. So the slope is there like that. And we use then that slope there to go there. So it avoids the curve, it gets over the error that we can't get from the curvature of the solution. I'm going to assert that these methods are first order accurate, second order accurate, in a minute, fourth order accurate. The way I find out how accurate they are is, as we did with finite differencing, you put in a Taylor series with lots and lots of terms in, and then find out what happens. Okay, so this is a second order accurate scheme, and I think this is on the handout somewhere. Okay, back on the handout. And it's implicit. So you see that we're trying to work out the first order. We're trying to find the time derivative in terms of the value. We're solving this equation, but we take the average of the value between a time level n and time level n plus 1. So this is sort of the value of the function at time level n plus a half, the middle. And this is first order time step from there, but it's actually centrally differenced around the half point. So this is sort of central differenced around the half point, and that's why it's second order accurate. But it is implicit because you have to know the answer to work out the answer. Okay, for this linear one-dimensional problem, it's quite easy to invert the matrix because there isn't one. And if you solve that equation, you find that you have here a 1 plus lambda delta t of un, and on this side you have a, sorry, it's a half because of the half. You have an n plus 1 and a minus half of delta t times lambda. And then we can do n time steps. So that expression there shows you immediately that in the case where the lambda is negative, it's a stable one, the real part is negative, then this is sort of 1 plus and that's 1 minus, so this is less than 1, so it decays. So it's stable for all delta t if lambda is negative. And in the case when lambda is imaginary, so this is 1 plus I, something, this is 1 minus I, so the magnitude of the top, the absolute value of the top, modulus of the top, is equal to the modulus of the bottom. So this is of magnitude 1. So when lambda is imaginary, then it is actually a cosine t behavior, and the amplitude should not change, and the amplitude with this numerical scheme does not change. So what you get wrong is the frequency of going round is delta t squared wrong. It goes around slightly slower than it should do. Okay, so this is another second order scheme which is explicit, and it's called leapfrog, and the idea is that we work out central time differencing, the time derivative at time level n, because we're feeding it information at time level n. So we use the time step before to get to the time step afterwards by centrally differencing around time level n. And there's 2 delta t's between those two. There's a problem with this method half the time. So the problem arises, we started with a first order ordinary differential equation. This numerical version is called a recurrence relation, and it's a second order system. It involves n plus 1, n, and n minus 1. So we've got a second order numerical question from a first order differential equation question. So we've introduced something that we shouldn't have, called a spurious solution. So I can solve this recurrence relation, and the general solution has coefficients a and b, and then there's theta plus and theta minus to the power n, where theta solves a quadratic equation, which I've solved. And then you can look to see what happens as delta t gets small. You find that the theta plus does the correct thing. It's n delta t, so that's t, e to the lambda t. That's the correct analytic solution. And then there's a second solution coming out of the b term. It probably started quite small because it only picks up errors as you evolve. It oscillates in time, typical of a numerical instability. It goes plus, minus. And if lambda is negative, then this is an exponentially growing solution. Okay? However, if lambda is purely imaginary, corresponding to a question where the answer is a constant oscillation, cos t, then it turns out that the two terms are not decaying or blowing up, but are oscillating, and this has a small coefficient because it started small. So it's quite safe and is used in purely oscillating problems, as we'll see later. Okay, so this is first order and second order methods, implicit and explicit methods. This is explicit and fourth order accurate. It's complicated. Okay, the anglicized version is Runge-Kuttos and wrong. So here we work out a little step using a time step and the derivative at time level n. Then we use that estimate of how far we go. We only go half the distance added to where we started, and we're at time level plus a half, and we get a second estimate, which we put back in again to find out, as a half step there at a half time here, to find out a third estimate of how far we want to go forward in time, which we put back in again with the full time, the full amount, and then we find a fourth estimate of how far we want to go forward in time, and then we take a weighted sum of them. And you have to know those blue coefficients, and you can code that up yourself. But MATLAB has got this in. If you ask for fourth order Runge-Kutta, it will do this for you. Okay, it's very good because it's fourth order accurate. It has a stability which is something like 3 divided by the size of lambda. And the really good thing is that if you decide your calculation is inaccurate, if you decide there's something interesting happening somewhere, you can change delta t immediately. So you can have a smaller delta t where you need it. And then you can go back to a big delta t when you don't need large, small delta t's. So it's very easy to change delta t at every time step. The problem is that I evaluated the derivative 1, 2, 3, 4 times. And evaluating the derivative might be inverting a Navier-Stokes problem in the background. I'm sorry, inverting, it may if it's come from a Navier-Stokes, inverting a Poisson problem. So working out the derivative could be a very expensive request. So you don't want to do it 4 times. And there are more ways to come. Anyway, pursuing this method, you can control the error. You can decide when do you want to make a smaller time step, and you do it in the following way. You make 2 time steps of each of delta t, and then you go back to the beginning, and you make 1 step of 2 delta t, and compare the difference. Now, if the error is if it's a fourth order scheme, it means the error in 1 time step is delta t to the 5th with some unknown coefficient. So if we go forward with 2 steps of delta t, we get 2 lots of this error. On the other hand, if we go forward with a single step of 2 delta t, we get 2 delta t to the power 5, which is 32. So this is 2b, and this is 32b. So if I can then take this combination of 16/15 minus 1/16, I actually can eliminate the b delta t to the 5th error, and I then get a 5th order accurate scheme. Moreover, I can see what is the size of this error here by taking the combination of 30th of the difference between the two. Because this is 32 and that is 2. Subtract them, I get 30 of them, divide by 30. I can see how big the error is and decide, is it time to make a smaller time step? So there are packages that you can use, and you should use packages rather than program all this up, which you say, get me an answer of accuracy of 10 to the minus 4, and it will integrate along, and it will find out what the error is and reduce the time step so it keeps the error always at 10 to the minus 4. Okay. That is the very commonly used explicit fourth order Runge-Kutta method. There are higher order schemes, lower order schemes. Actually, the midpoint is effectively a Runge-Kutta second order scheme. And there are implicit ones. I would never think of using this. It's a total mess. So it is, you go from time level n to time level n plus 1 with 2 estimates of how far you want to change, and they're embedded in the interior here of these calculations of the derivatives. So you don't know what delta u1 and delta u2 are, and you have to solve this nonlinear question for those 2. It's a ridiculous method. Should never be thought of. Right, move on. So the Runge-Kutta method has 4 function evaluations which could be expensive. In cases when they're very expensive, there's another totally different approach, which is called multi-step. So we go from time level n to n plus 1 using information about the derivative now at time level n, but we also use the time derivative 1 step before and 1 step before that. So if you know the time derivative at 3 places, you can fit a polynomial through those time derivatives. polynomial in time through those time derivatives, and then you can integrate that polynomial in the extrapolation from n to n plus 1 and arrive at n plus 1 better than doing a straight line. So working out all, for this very much for equispaced points, working out what that polynomial is, doing the integral in time, arrives at these rather strange coefficients of 23, 16, 5 divided by 12. So that's explicit. We only use information at time level n and previous to go forward, and it's called Adams-Bashford. There's another one, Adams-Moulton, which is implicit. So we go from time level n to n plus 1, using information about the derivative now, one step before, 2 steps before, but also at the new time where we don't know what the answer is. So it's implicit and is fourth order because we are using 4 data points. Okay, what we typically do is actually, there's a predictor corrector method. We use the top method to get a fairly good estimate of what the future is, use that to work out the derivative here to get a better estimate. So this is third order information into here, but because of the delta t, the errors from that, the third order errors from that, multiplied by delta t become fourth order errors, consistent with the fourth order errors we had before. So it does involve 2 function evaluations, but it gives you a fourth order. So it's half the function evaluations to fourth order Runge-Kutta. So these methods separately, rather than in combination, are just one function evaluation per time step, which is good. The big problem is I'm using previous information. How did I get off the beginning when there's nothing before the beginning? So you have to use some other method to get going, like the Runge-Kutta, or you can do a Taylor series expansion, or you could use first order accurate methods, but with really tiny time steps. So you've got to get some information before you can use previous time steps. And then there's a problem. Suppose you want to change delta t, because you know from the physics you're engineering, you're arriving at some interesting point and you should resolve it more carefully. These are very much based on fixed equi-time steps. So in fact there is a way out, because as I explained, what we do is we put a polynomial through the derivatives, polynomial in time. If I know a polynomial in time, I can work out the function at any time I like. So I could evaluate it at equispaced points, but more closely equispaced points, ready to change the time. But it's a lot of work. It's very fashionable. There are things called symplectic integrations. So this is for non-dissipative systems. Most real physics has got friction in, and that's good because you have to apply force to keep it going, and then you get it's very insensitive to your numerical errors. There are much more mathematicians and physicists are interested in perfect systems without any friction. Then you have to make sure that your numerics doesn't have any artificial friction, because your numerics will grind to a stop where the original problem doesn't. So that's what these are all about. Now, it's all to do with Hamiltonians. So does anyone know what a Hamiltonian system is? Any sort of, no, 1 or 2 people, cautiously. So you can recast, and I'm not going to do this on the board, you can recast Newtonian dynamics, the rate of change of momentum equals forces, into an energy formulation that's the energy, which is fancily called the Hamiltonian, expressed in terms of the momentum squared and spring constant, potential energy squared. and then you take a derivative of the Hamiltonian, Hamiltonian with respect to the momentum that tells you how the variable changes, and a derivative with respect to the variable that tells you how the momentum changes. That's these equations. The momentum changes according to how the potential energy changes with position, and the position changes in terms of what the speed is, which is what the momentum is, which is what the derivative of the Hamiltonian, the energy, is with respect to momentum. Okay, very vaguely. And these have the property, these equations, written out in as many dimensions as you would like, that the volume of a little piece of, you have a little solution, you're at solution at a point, but if you have a solution with delta Q there and delta P there, these methods which evolve your solution here will preserve the volume of this element. And that means you're preserving the energy so that your solution won't run to a stop with artificial numerical friction. And the way they do it is, here's a symplectic integrator. It is actually leapfrog, which I said you should be sort of avoiding. And it really is used in molecular dynamics. So molecular dynamics integrate Newton's equations of motion for molecules with things like van der Waals forces between them. So we can simulate a gas in motion. They do much more than this. So this is non-quantum. You simulate molecules in a membrane. And your calculation may take, I've heard it takes 6 months on 50 computers simultaneously to integrate forward 1 picosecond of a membrane with several hundred molecules in this membrane. Right. So what you do is you integrate this equation, half a time step. So we know the derivative here. So this would be the force. This is the derivative of the energy with respect to the variable. So it's the derivative of the potential energy in space, which is equal to the force. And then you integrate from n to n plus 1 the position, and then you integrate the momentum from the half that you already got forward in time. So in the first step, I change P. So we've got here P upwards and Q sideways. So in the first one, I keep Q fixed and I change P. So I change it to a parallelogram. Essentially this and this go to there. Whoops. The area of that parallelogram is the original area because I've just sheared it. In the second step, we move in this direction. So let me go back to this thing. We essentially take a box like this and we move it to there and there. Again, we've taken our box and sheared it, so we've not changed the area. So I'm preserving the volume in PQ space. Okay. And finally, the Navier-Stokes equations. So in time integrating the Navier-Stokes equations, if you want to go to higher order accuracy like delta t squared, I'll show you a delta t squared. Before we had just simple delta t. You can do different things on different terms. Quite permitted. So what this is doing is going to use u dot grad u is going to, we're going to go from time level n to time level n plus 1. And so I want to know what the time derivative, this is a time derivative centered on n plus a half. So I'll work out u dot grad u at n plus a half. And I do that with an Adams-Bashforth multi-step method. So that's got u dot grad u under control. And then for the For del squared, this is finite difference of del squared, but I'm doing it at time level n and time level n plus 1 and taking an average. So I've worked out del squared at time level n plus a half. So this is a central differencing at time level n plus a half, so it's second order accurate. And I'm using one method for the del squared and one for the u dot grad u term. There's an alternative. We're going to do with this next time when we get to hyperbolic methods. And there's a nice zigzag method, which I'm not going to talk about it. Right. Okay, and then if u dot grad u is very important to you, you should use Lagrangian methods. You should actually, u dot grad u says moving with the flow. Well, why don't you invent a numerical method which moves with the flow? If that really is the big dominant term in what's happening. So there are finite elements. I showed you a finite element I used in granular flows where the finite mesh, element mesh, moved with the flow. It does a fantastic job with u dot grad u. Right, so we had then there's how do you deal with pressure. I mean, it's done by a half-step method. You make a time step, a split time step method. You make a time step with no pressure, and then you do the time step with the pressure. But this is doing it a second order accuracy. So before we made, and this picture is quite good. So we were on some surface. We knew we had to go sideways, and we went sideways, but then we projected back on. And that introduces first order errors. So this one says we're going to go to the new split time with the u dot grad u and del squared u, and but we'll use the pressure at the previous time step at time level n plus minus half, because we're here thinking at time level n plus a half. So this is an estimate of the pressure from before, and it's only delta T wrong. So we're then going to calculate the extra new bit of pressure, and it's only a little bit. So if we do first order accurate estimate of the little bit, we actually end up with second order accuracy. Right, it is not simple. So the idea is we go from this split time halfway there and add on something that looks like pressure. It is not pressure. And it's only going to be a little thing. And we choose particularly this thing where we add on so that the divergence of the new flow is strictly zero. So that means it's got to be the divergence, or del squared of this has got to be the divergence of, which that is not zero, and we'd like it to be zero, and there's a delta T comes on. And there's always a question of the normal boundary conditions. We've discussed what is the normal pressure condition, and it is that the normal derivative of this is the normal derivative of the boundary condition, which is probably no flow, the normal component into the, so this is probably zero, your boundary condition, and whatever you got out of this calculation on the normal velocity, which will be non-zero. So this will correct for that. And then when you've solved this, you add, when you've solved for phi n plus 1, you put it into here to find out the new velocity field, and you update the pressure. But phi is not the pressure. Phi, the new pressure, is the old pressure plus the gradient of phi, and then a little bit that comes out of putting this correction to u into there. That gives us this, and because del squared is not equal to 0, there is a term there. There's only a half because there's only a half there. Okay. Now, one of the problems, first order problems, which we want to get rid of if we're going to have a second order problem, is if you make the split time step and then add a pressure correction, this pressure gradient could be along the boundary, so you may have messed up the tangential boundary condition. So the way of getting around that is to apply a boundary condition on this split time step, not that it's 0, no slip, but it's equal to the given boundary condition, the no-slip condition, but plus what you'd got for phi at the time step before, what the extra pressure gradient you'd added last time along the boundary. We anticipate it, and we get ready to have the same thing again. It's not quite the same thing, but the difference is small. Okay, so that is a second order scheme, and it's called pressure update because we update, we keep with a running estimate of the pressure, and we just update it with a small thing each time, which is much better than making a wild jump and pulling back a big amount with pressure projection. Right, I think that's it. That's time stepping on its own. Anyone have a question? There are lots of methods there, and now you know there's lots of methods. You can look up in books and find even more methods. There are lots of Runge-Kutta, there are lots of multi-step methods. What's happening tomorrow is there'll be a numerical analysis. Linear algebra. So solving AX equals B, and also looking at the eigenvalues of A. There's a lot of different methods and details there, all summed up in 60 minutes. And then there will be 2 lectures on hyperbolic equations, which are not good for you. The best thing is for me to say, never do it, and then I wouldn't have to lecture at all, and you'll be much safer. But we'll do hyperbolic equations in 2 lectures. So tomorrow, the linear algebra is part of the general issues that you always come across and you should all know about. After that, we get to specialized topics which you may be interested in one of the 5 different special topics, 6 different special topics I'm covering. You may not be interested in any of them, but they're specialized topics. Okay? Any questions now? Okay, stop. Switch off the mic.